All right, hello and welcome to the last lesson of Unit B. We're on 19B. Today, students will be able to determine where a graph is increasing, decreasing, linear or nonlinear. There's also constant in here as well. Remember, increasing means it's going up from left to right or a positive slope. Decreasing means it would be going down from left to right or a negative slope. Students will be able to describe where a graph is increasing, decreasing, linear, or nonlinear. And this is important for reading graphs and interpreting what the data represents. So let's look at this very first one. We'll see some different sections to these graphs, and they don't necessarily have one equation that would go with them. And so we might be able to make an equation for each separate little section here, but this does not have one equation that goes with it. This is a situational graph. And so this shows the varying speeds at which Emma exercises her horse. Okay, so Emma has a horse. So at what point was Emma's horse increasing its speed? So increasing here means we're looking for the portions of the graph that are going up from left to right. And so what I like to do is highlight the different sections. So right here, it is not increasing from 0 to 10. That's staying constant. It's staying at a 0 slope, but it is increasing from 10 to about 17. If I read the next part, that looks like it's staying the same. Reading the next part is decreasing. Reading this part staying the same. So the only portion here that's increasing is the portion from the 10-minute mark to about the 17-minute mark. So at what point is the horse increasing its speed? We would say from the point 10, it looks like 10 approximately, that's less than 5, so 10:4. To approximately, that's about 17 right there. Don't mind the bell. 17:25. So it looks like it's increasing in this portion here, just from the 10-minute mark to the 17-minute mark. At what point was Emma's horse decreasing its speed? So I'm going to change the color here. You can do this if you have your own highlighters. Looks like it's decreasing in this little portion right there. So at what point is that decreasing? Well, let's see, that's 35, so that looks like it's about 36 at the 36-minute mark. It was at 25 miles per hour to about the 40-minute mark. 40 minutes looks like it's back to about 4 miles an hour. So that's where it was decreasing its speed. In other words, a negative slope. If we were to find the change in y over change in x, this would be a negative slope, and this would be a positive slope. So we can even write that in, positive slope and negative slope. Because slope is the rate of change, it's how it's changing. Increasing can describe that it's changing by going up. Decreasing can describe that it's going down. It is changing by going down. At what point was Emma's horse moving at a constant speed? So she was constant at 0 to 10 minutes. So from 0 to 10 minutes, she stayed at 4 miles per hour. So from 0:4 to, let's see, 10:4. Notice that's a 0 slope, no change in the y's. From 0:4 to 10:4, she stayed constant. Looks like it's from 17. At 17 minutes, she was at 25 miles an hour. So after 17 minutes, it was 25 miles an hour to about, what did we say that was before? We said that was 36 to 36. She was still at 25 miles per hour. And then there's another constant portion here at the 40-minute mark. So from 40 minutes, at the 40-minute mark, she was back at 4 miles per hour. And she stayed that way until the 50-minute mark. So 50 minutes, she was still 4 miles per hour. In other words, the constant speed would be a 0 slope. 0 slope. So if you think of Slope Dude, this is 0 fun. That's the constant portions. All right, so that's what we're doing today. We're reading graphs. We're just looking for where it's constant, increasing, constant, decreasing, constant again. And we always want to look at what they're comparing. So here they're comparing speed to time. So now let's look at some graphs that are already done for us. The height of a tree increases over time, but not as a constant rate. Which graph best shows this? So does this one show increasing? No, this is constant. This one's constant. It's staying the same. So if you follow this, that's showing that it's staying the same height all the time. Here we see this height increase, and it's still increasing in these little portions here. It's just increasing at a different rate, and so that would be this graph. That would be describing this graph. Constant rate. So let's go ahead and highlight a little bit, if you have your highlighter, increasing over time, but not at a constant rate. So it's increasing, it's just not linear. All right, let's look at number 3. The dimensions of the basketball court have changed over the years. However, the height of the basket has not changed. Which graph best shows this? So we're looking at the height of the basket not changing. The height of the basket has not changed over time. So if it has not changed, that's a constant graph. So it's staying the same height over time. This one is showing an increase. So we want this one. This is the one that's showing the constant rate over time, the height staying the same. All right, let's look at number 4, because this one looks a little bit different. It says a ball is tossed into the air. Which best shows this? Which graph best shows this? So we either see the ball go up and then kind of float for maybe a second, less than a second, and then come back down, or we see it increase its elevation, stay at that point for a long time, and then come down? No. No, basketballs don't float in the air, so it doesn't float. No floating. This is not a floating basketball. No floating. That's what that would mean. And so the one that best shows this would be this graph. All right, so now let's make our own. Number 5, it says the school is 100 meters from Alicia's house. So we see the distance from home goes from 0 to 100 meters from home. And then we're going to be graphing it according to time in minutes. And it says the following describes the most recent trip. So we just take each of these little portions and we graph them. She walked 25 meters, so we need that, 25 meters towards school in 1 minute. Okay, that's our first amount. So she got 25 meters away in 1 minute. So after 1 minute, I'm going to follow this up to the 25-minute mark. Now, before she left home, was she any distance away? No. So she should be starting at 0, 0, because before she left, she was not a distance away from her house. So let's go ahead and graph just from those 2 points. That's the first little section. Now let's look at the rest of the information. It says, Alicia realized that she left her iPad at home. She turned around and walked home at the same speed. Okay, so she turned around and walked back home at the same speed. That means her distance from home is going to decrease, and it's the same speed, which means it took her 1 minute to get back. So now she's back home over here. So we can see the x-axis down here would be like home, and up here would be school. So she walked away from home 25 meters, then she turned around, walked back home because she left her iPad there. She spent 5 minutes looking for her iPad. So for 5 minutes, her distance from home didn't change. Don't mind that bell. For 5 minutes, her distance from home didn't change. So that means we're going to count 5 minutes. 1, 2, 3, 4, 5. So right here at the 7-minute mark, she's going to be staying at home. So right here, that's her distance from home isn't changing. She's going to stay there because she's looking for her iPad. Then she walked all the way to school at twice her original speed. Okay, so she was booking it. She walked really fast. Well, her original speed was 25 meters in 1 minute. Let's call that meters in 1 minute. Okay, so her speed is 25 meters per minute. So that means in 1 minute, she goes 25 meters. I'm going to go ahead and put a point there. 1 minute is 25 meters. Another minute is another 25, so at 8 minutes. And let's go ahead, let's make a table out of this, because I think that's going to make it easy to find these other points here. So 1 minute was 25 meters. 2 more minutes would be 50. 3 minutes would be 75, and we need to get to 100, so that would take her up to 4 minutes away. So I'm going to be adding 4 total minutes to this time right here. So that means 1 minute away, or 1 more minute was 25 away. Another minute from there would bring her up to 50. Another minute from there would bring her up to 75. And another minute from there would get her to 100, would get her all the way to school. So she was walking at 25 meters per minute for an additional 4 minutes. All right, so after all that time, oops, of course my line is a little bit crooked. After all that time walking, she finally made it to school, and then she stayed there. So we're just going to continue the rest of this graph as though she were staying at school for the rest of the given time. So I'm going to make a constant line up here. Let's make sure I line that up right. I'm going to make a constant line because she's staying at school now. And we don't know when she left for home. And so I'm going to put a little arrow there because she stays at school until the school day's over. So we see some increasing portions, decrease, she turned back and went home. Then she stayed home looking for her iPad. And then finally she walked to school, 25 meters per minute, all the way until she was at school, and then she stayed at school. So that's how we graph a situation. All right, let's go ahead and try that again. These are kind of fun. They're like little graphing stories. Wade parked his car in the supermarket parking lot and walked into the store. We're going to be graphing the distance from the car and time in minutes. All right, so that means at 0, he is still at his car, and so I'm going to put a point right here at 0, 0, because he hasn't left his car before time has started. It took him 2 minutes to walk 60 feet. It took him 2 minutes to walk 60 feet into the store and to the customer service counter, where he waited in line for 1 minute to pay his electric bill. So I see this first part, 2 minutes to walk 60 feet. 2 minutes goes to 60 feet. All right, so we're going to graph roughly from there to there. All right, it took him 2 minutes to walk 60 feet to the store and to the customer service counter, where he waited in line for 1 minute. So he's not going anywhere. He waits in line for 1 minute. So he's going to stay right there at a constant distance from his car. Next, he walked 60 feet to the back of the store to get 2 gallons of milk, which took 3 minutes. Okay, so it took him 3 minutes to walk 60 more feet. So 60 and 60, let's put a point there. 60 and 60 would be 120, and it took him 3 more minutes. So 1, 2, 3 more minutes to get up to the 120 point. All right, so let's connect that. Again, we're just graphing his distance from the car. So let's go ahead and get that point there. So I can see he walked away from the car cashier. He waited in line for a minute. Then he walked to the back of the store. It took him 3 minutes to get to the back of the store. And he got his milk. Don't mind that bell again. Then he grabbed the milk and turned right around. So he's not going to hang out here. He's not going to hang out at this distance and watch the milk. And so he turned around, walked 50 feet to the checkout near the front of the store to pay for them, which took him 3 minutes. So he walked back 50 feet to the checkout, which took him 3 minutes. So he's going back closer to his car now, 50 feet. So let's see, 120 minus 50, that means he's going to be down here at the 70-foot mark. And it took him 3 minutes. So 1, 2, 3 minutes, down here 50 feet. So I'm just going from where I was, and I keep adding to the graph as long as they keep telling me information about how far he is away from his car. So he walked back 50 feet, so 50 feet closer to his car, brought him down to the 70-foot mark, and that took him 3 more minutes. After waiting his turn for 3 minutes, so he waited for 3 minutes. Waiting for 3 minutes means his distance away is going to stay constant for 3 minutes. 1, 2, 3. So he waited there. There's the waiting for 3 minutes. And paying for the milk, he walked 70 feet back to his car in 4 minutes. So it took him 4 minutes to get all the way back down to his car. All right, so let's count 4 minutes. 1, 2, 3, 4 minutes to get all the way back down to his car, which is at a distance of 0. So right down here. And so I'm going to connect those. That's how long it took him to get back to his car. There he is. And then as far as we know, he stays in his car, and so that would continue that way. All right, so there's our little story. Again, we see the 2 minutes to walk to the counter, 2 minutes or 1 minute waiting in line, 3 minutes to the back of the store, 3 minutes back to the counter, waiting in line, and then finally back to his car. All right, analyze these graphs. When did the first growth spurt occur? So it looks like this one. I'm going to try to do that because these are nonlinear equations. It's okay. So it looks like the first growth spurt occurred from 0 to 8 years. 0 to 8 years looks like the first big growth spurt. And then it looks like it's still increasing, but at a slower rate right here. What occurred at ages 17 to 21? So from 17 to 21, it looks like your growth, looks like the average height stays constant. So we'll write height stays constant. Explain why this graph doesn't show a decline up to age 21. Well, we don't shrink. This is talking about height. We don't shrink. All right, so we read a graph by looking at it from left to right and then judging what it's comparing, years to height, distance to the car, and time. Go ahead and try the exit ticket today, and as always, make sure that you ask me if you're not sure how to answer these questions. Good luck, try your best, yay math.